And yeah, well, so yeah, hi everyone. We're gonna resume our reading group, right? So we have a set of 10 papers, for the upcoming like 2.5, 3 months. And we start with this lovely paper, the Occam's razor for distributed protocols, right? So I apologize, I don't really have like slides and presentation. So I'm gonna kind of improvise as we go. So what this paper is, um, I think it's a really interesting educational paper, right? So like it teaches a way to try to think about the systems and algorithms and how they interact in a way that may allow you to uncover some optimizations, right? I personally don't think that the optimizations that they uncovered are that new. I think what they did is something that we kind of already know, right? But there is like a systematic approach to how they uncovered those optimizations, right? And hopefully you can apply the same kind of systematic approach to other algorithms, other distributed systems, and hopefully again it will help you, right? But at the very least, it's a way to like reason about distributed systems and the interactions within them. So the paper talks about the paper mostly focuses on replication protocols, right? Like actually, it mostly focuses on one example, which is using Paxos and two-phase commit in systems like Spanner, right, or like any transactional distributed systems. And they use that Paxos and two-phase commit as kind of test bed for their reasoning framework, right? Um, so to kind of go into the details and to give enough background, they start with 2PC and Paxos, right? So they kind of go over the process of like a basic, almost naive implementation of two-phase commit on top of multi-Paxos based replicated state machines, right? So and they go with this setup where they have 3 regions, right? And they go through like a life cycle of a transaction, right? So at least a life cycle of a transaction from the time it starts to prepare, right? So when the client is ready to run the transaction, right? They will submit it to the coordinator, right? The coordinator, one node, and in a so in this case it's replicated, right? Everything is replicated like 3 ways, right, in 3 different regions, or AZ, so however you want to replicate, right? But here we have the coordinator. It will run this prepare, right? Obviously it goes to like other regions and other partitions, right? These other partitions shown here, they have to enter that prepare in their like respective logs, and these partitions are also like replicated, so they run Paxos for that. Once they are prepared, presumably they vote yes, so that vote is delivered back to the coordinator. Then the coordinator essentially will replicate that commit decision, right? Since we had like all yeses vote, and once it's durably replicated in coordinators, state machine, right? We can kind of return to the client saying, okay, your transaction is durable, and then asynchronously maybe tell other partitions, okay, transaction is durable, please, apply it, release locks and whatnot. Right, so kind of the basic process, right? I think what the paper tries to emphasize and what the authors try to emphasize is like in this process, there is a lot of like stuff that kind of goes in sequence, right? And some stuff that happens to be like that occurs in parallel, right? And there is a lot of replication involved here as well, right? And different state machines, different Paxos boxes and whatnot. So their reasoning, their approach to try to figure out those the optimizations is like this, right? So they think that a lot of protocols, a lot of algorithms have unnecessary sequential steps. Right. So, and if we can remove some sequential steps, if we can make some things that happen sequentially, and if we can make them happen in parallel, right, then we can reduce maybe the latency or the lock holding times, right? So, which is beneficial, both from, let's say, a client perspective, right? If we reduce the latency or, lock holding time, will be beneficial also for clients and for the system itself, right? So like less lock duration means less contention and less transaction aborts and retries and things like that, right? So if we have steps in this process that are done sequentially but can be parallelized without impacting the liveness and without impacting safety, right, then that would be an optimization we want. And their framework tries to find those steps, right? So let me go to the way they try to like reason, the way they suggest to reason about the systems, right? Here they show the same protocol, but they try to express it in terms of the messages that a particular node, they call them transducers. I'm not really going to stick to their terminology so much, but they express it like a node can send a message and the node can update a state, right? So message, state, right? So everything that a node or transducer does is it updates its local state and it sends messages to other nodes, slash transducers. Right. So they try to express those algorithms in terms of those two things, right? Like what is being communicated and what local state is being changed. Right. So should be simple so far. That's not a very big kind of leap to make from the previous figure that I showed. Once you kind of start to reason about your distributed systems as nodes that send messages and exchange local state, they say that, what they want to do is they want to uncover something that they call weak dependencies, right? So the weak dependencies are sequential steps. So let's say node A sends something to B, B sends to C, right? So, you have sequential like steps A, B, C. And if it's possible to change the algorithm in such a way that you can send something from A to C and A to B in parallel, if you don't need to like preserve that sequentiality, they say that it's a weak dependency, right? And like more formally, they say that since let's say A goes to B and goes to C, right? Whatever C has, right? Like whenever C receives the message from B, if that message that C receives from B is derived purely from the message that B received from A and doesn't involve any local state at B, right? Then you can technically send the same message to C and have C, derive, what it needs to from that message, right? So that's kind of the big thing, right? Like that they try to say, if that message that B sends to C doesn't involve the local state at B, then you don't necessarily have to send, that stuff through B, right? So that's what they call the C1 rule, right? So that's essentially saying that I can send data directly to C and have C derived whatever state it needs to bypassing the B, right? Because that transition doesn't involve the state of B itself. Now, there is other problem, right? So that's one criteria for weak dependency. The second criteria is essentially, once you start doing this, once you start making things in parallel, you also need to make sure that you always have B in the execution path, right? Because now, like if you ever in original, code, right? If you ever reach C, it means you had to go through, transducer B, right? But in the parallelized version, you can reach C without going to B. So, you still need to do what B kind of does because B carries its like local state and whatnot. So you need to guarantee that, bypassing this C, bypassing going through B to C, will still invoke B all the time, right? I think what they say, like in practice, it means that B needs to be durable, like a replicated service, right? So if that's going to be the case, then you like if you send message to B and B is unfollowable, then you will have B regardless. So these are the two rules, right, that define what weak dependency is. And I've already mentioned kind of the way you go around this weak dependency is you bypass it, right? You have the A send the message to C directly. And that's what they express here, like new rules. However, there is this weak dependency, it's still a dependency, right? Like it was there for a reason, right? So if it was that easily bypassable, people would have probably done that already, right? So it's not like, super rocket science. So there is a danger that lurks in that C. And that danger is, what if C obviously sends more messages, right? And C can send messages, but I can get from A to C and then C some messages while B hasn't been done yet, right? But whatever C sends in the original algorithm, the B had to be done by the time that message is dispatched from C. So what they also say is essentially we need to put a barrier here, right? That will wait for the B's completion and C's completion before the message dispatched from C can actually proceed, to the next node. And I think that's kind of all there is to it. And I will go to the example, and I think the example will make it a lot clear, like a lot easier to grasp. So we're back to our two-phase commit, Paxos with two-phase commit, right? And this is the original, again, the third version of that algorithm that they redraw in like the third figure. And you go start the prepare, right? It goes to other participants. These other participants run, their prepare, it kind of emits the replication now, for the brevity. Once, these other participants are ready, they vote. Those votes go to the coordinator. Coordinator decide whether it's abort commit, and then, learns itself, and the user learns, and then the other participants learn that okay, the outcome of the transaction, right? So, and what they say is this three steps, like this flow right here, from prepare to decide, and from decide to learn, is an example of a weak dependency, right? So this is my A, this is B, this is C, and they say that we can go directly from A to C, and essentially learn the outcome of the transaction, right? At all the partitions. And if you look at this, that's kind of what they do here, right? So okay, the reason why you can do it is because the decision is based purely on vote, right? So if the node who decides the outcome can count votes, so does everyone else can count votes, right? So and that's what they do here, right? So they send the votes to the learn transducers, right? As long as well as the coordinator, and they kind of collapse those two steps. And if you really look at this, right, this is nothing else but the like the learner parent that we have in things like Paxos and other state machine replication, right, where you don't have to learn the outcome from the leader. You can learn the outcome just by observing the votes. So with all that approach they designed, they really, in this case, were able to get to the learner pattern that should be like well familiar for distributed systems people. And they show the impacts this has on performance, and they go and show that there are more applications of their like framework reasoning that exists in this Paxos plus two-phase commit. One of them is kind of interesting, so where they replace one link with like essentially optimized a little bit of the data transfer to have the data transfer local instead of remote, but just to one server. And I'm not gonna spend too much time on this, but they also did the learner pattern in like multi-Paxos, right? So when they looked inside what happens on all of this like quorum counting and whatnot, and then learning outcome of the quorum, they just implemented the learner pattern again, right? So they have learner pattern in one of the places in 2PC and learner pattern in the actual like multi-Paxos. So yeah, arguably not very like well known, not very like groundbreaking optimization. We know how these things work, but they argue that like with their like reasoning approach, right? You can actually write models. They also say like TLA and whatnot, and have and use the models and use the tools to help you find those weak dependencies C1 and C2, and use the tools to also like change those models and model check them if you're like not convinced. So yeah, again, for every thing that they do, there is like a little bit of a performance improvement, a little bit of performance improvement in terms of yeah, the throughput and latency and whatnot. So yeah, the paper also talks about a few other algorithms that they used, a few other distributed data intensive systems that they applied their like reasoning to, where they uncovered other reductions that they can do that are not necessarily that learner pattern. But I'm not going to go into details for the sake of brevity. So yeah, I think I will stop at this point, and we can try to discuss.